Okay, let's do some proofs. I love some proofs. Okay, so we're going to approach this proof in a kind of different way stylistically than maybe you've seen in the past. So we're going to kind of use the same steps, so like the big general steps, like the whole idea of like brainstorming and writing an outline and like a rough draft before your final draft. Like that's going to stay put here in terms of your proof writing. But we're going to do it kind of in the classic mathematically nice way in the sense that we're going to try to shortcut a bunch of stuff. Not because we're lazy, but because we're being efficient. But anyway, let's get a sense of what in the world we're being asked to prove here. So we're trying to prove two triangles are congruent, ABC and ADC. So A up to B over to C. We want to try to prove is congruent to ADC, so we have A down to D over to C. So the first thing we should do is again get a sense of what we're trying to prove. We just did it. We're trying to prove that this green is congruent to this purple, but also what we actually have to prove this. So since we're dealing with triangles, the thing that should pop into our mind almost immediately is that we're dealing with proving or at least meeting one of these conditions. So what I mean is SAS for side angle side, side, angle, and of course angle side. If I can show in the purple and green triangles that we have this information that's matching and congruent, corresponding and congruent, we're good to go. So we might want to do some kind of preliminary thinking. Now we're kind of entering the visualization uh, part of the brainstorm. Is well, which of these conditions can I actually meet? Well, I'm given that BC is congruent to CD. So we should probably go ahead and mark our picture. BC line segment, I'm going to mark with one arc, and CD, again, one little mark here as well, because we're actually given that as congruent. And then we have AC bisecting BCD. Well, BCD goes from BC to D, and then AC, this line in the middle, bisects it. So again, I'm just kind of thinking ahead. Well, that's going to give us two congruent angles, uh, the one at 1 and the one at 2, because that's what actually means to bisect. To bisect means to cut into two congruent parts. Therefore, angle 1 and angle 2 are going to be congruent. Well, if you're looking at what we got already, I have a side and I have an angle, and I have a matching angle and matching corresponding side in the green triangle. So right away, I know I'm not going to use side. Um, what I need to determine now is what else am I going to use? Well, I have a side and an angle in a row. If I can find some other one more piece of information, I am set to write my proof. Uh, if we look at the angle at B and the angle at D, that's going to be a non-starter simply because I don't have any information about those angles. They kind of look right, but we don't know if this is to scale or not. In fact, we can't assume it. So even though they look right, I don't have anything that forces them to be right. So these angles are a no-go. I could look at these angles as well, but I don't have any information about the angles at A. I was told that AC bisects the C cluster, not the other way around, so I don't really have information either about those two angles. So my last hope is I can find some sides because I think I'm stuck on angles, which also means that I can't use these guys. So really my only hope is to somehow find another side length. Well, these two side lengths are again a no-go because just don't have any information that can take me to those side lengths. I haven't been given anything over here besides what I've already marked. So my really only hope of proving this is to prove something about this side. Well, hopefully this is going to be recognition for you. This should totally be congruent in both triangles because of the reflexive property. Okay? So if I'm thinking about how this is going to go, I'm going to use side angle side to prove this is going to be, excuse me, to prove that these two triangles are going to be congruent. Okay. So I have side and angle and side. So now I'm ready to kind of write this proof, but I'm going to write it kind of in a different style. So like that if-then structure is wonderful for kind of logically kind of conversing with someone about a proof, but it's not so great if you're actually trying to write the proof. It's very cumbersome. There's lots of repetitive sentences you have to write over and over again, and it gets pretty confusing just because of the volume you have to actually write. So again, if you think about what's the important part of that proof, is really the conclusion. So like we have to assume we're meeting the initial conditions, meeting the hypothesis, It's all about the conclusions in terms of proof writing. That's the part that gets carried over and used again. So I'm going to introduce you to a different style of proof. I'm going to call this one a flow style proof. And you're going to see why right away why flow style might be really applicable for this kind of thing. So before we actually write a proof, let's think about like a general plan for a proof. So we're going to prove these triangles are congruent by side angle side, okay? Triangle congruence. And the way we're going to do that, the way we're going to meet that condition, well, I know that one side was actually given to us. I know that one angle was a result of a bisector. And then I know that the last side was the result of reflection, REF. So that's kind of how I'm going to meet that condition. Once I can show those three things have happened, I have my congruency. So let's actually write this proof. So when I call it a flow style, I'm actually going to emulate this plan actually really, really carefully. So here's how this is gonna look. So this is actually my proof now. So to prove triangle ABC is congruent to triangle ADC, I know I'm going to have to show three separate pieces. I have to show that I have a side. I have to show that I have an angle, and I have to show that I have another side. Okay? So let's start with this one. So side one, I actually have to name it here. So in my plan, I just said, well, I'm going to have a side that's given. Well, here I actually have to name them. We have BC congruent to DC, and that's actually right here in our given statement. So I know that BC is congruent to DC because it was actually just given to us. Oh, that's messy. Okay. So that's good. I mean, we definitely have one side length down. We just have two more pieces to go. Let's talk about this angle. Well, again, the angle 1 and angle 2, came from the result of bisection. So I can claim angle 1 is congruent to angle 2, and that's going to be because the definition of bisector. Okay? So I have claimed that the angles are congruent. I've told you why. Angles are good to go. And so the last bit is going to be side 2. So side 2 occurs right here in the middle. I'm trying to highlight it. I hope you can see that. So AC being congruent to AC. The reason why is going to be because of the reflexive property. Okay. So I had to show the triangles were congruent, I had to show side angle side. I've shown that I have a corresponding matching congruent side angle side. So now I can actually make my final conclusion. And again, because we call this a flow style proof, I'm going to treat this like a flow diagram. So my conclusion, if I combine these three pieces, and that's what the arrows imply that I'm combining, I can conclude that triangle ABC is congruent to triangle ADC because of the side angle side triangle congruence theorem. And we are done. And that's actually all there is to this proof. So again, we've shown that we have side angle side. We made the statement of congruence. We told us why that's got to be so. Those ideas come together. Bam, I can make my conclusion that the triangles are congruent. I told you guys why, side angle side, and QED signs off. And really, that's all there is to this proof. So good luck at number 2.